Welcome everyone to the AMPC webinar around integrated wastewater treatment and bioresource recovery. We'd first like to begin with acknowledging the traditional owners of the lands on which we all meet today, and I'd like to pay my respects to elders past and present. So today our panel of presenters, ourselves obviously, AMPC, the project sponsor. We also have ARENA as a project sponsor on this project, so we acknowledge their financial support, and Bindaree Food Group as the grant recipient and the subject site that this project was conducted for. The webinar presenter is Dr. Fabiana Tessely from Tessely Consultants, who was also the project provider. Just some housekeeping before we start. The webinar will go for 1.5 hours. So Fabiana will present for about an hour, and then we'll have half an hour of Q&A. And Chris Edwards from Bindaree Food Group is here with us today to help answer questions in the Q&A. Just before I hand over to Fabiana, I'd just like to recap on why this FEED study was completed. So anyone who knows our decarbonisation work by AMPC will know that we've assessed the different technologies that are required by the red meat processor sector to achieve decarbonisation by 2050. And bioenergy plays a major role in that decarbonisation task. Around 27% of the total decarbonisation task will be bioenergy solutions. So this project, as a result, is an important step on that sectoral decarbonisation for Scope 1 and 2 emissions. In other words, emissions that are under operational control of red meat processors. And this project also looked at cost benefits and co-benefits that come from bioresource recovery. So I'd just like to hand over to Fabiana. Thanks, Fabiana.
Thank you, Matt. Yeah, good morning and good afternoon, everyone. Yeah, I'm here to present, which is the conclusion of a very long journey that we had with Bindaree, which started probably almost 3 years ago. So this project here, we looked at their operations and how can we better recover value from the streams that were considered wastes, and of course converting them into byproducts where we can recover value, right? So the project, as Matt mentioned, was co-funded by AMPC and ARENA and was concluded in August 2024. So you can see here is obviously an AI created image where we integrate agriculture and industrial processes in a circular economy framework, right? Besides sharing the outcomes of the project with Bindaree Food Group, we are also going to give a bit of an update on our latest trip to Europe, where we went to see the real life cases of this kind of technologies being applied in full scale by farmers and producers. So the context for this presentation, I will start with the project drivers, and then I'm going to explain in more detail what is the bioresource recovery concept and also how that connects with other projects we are developing with AMPC. And then I go through the project methodology, how we develop the concept, and then present the numbers, the outcomes that came from the case study from Bindaree. And then I'll present a summary and the details of our European tour, and we'll have space for answering questions together with Chris from Bindaree. So just to put this in context, yeah, we start looking at one small facility in, or not a small facility, but one processing facility in New South Wales. But then that reflects into the outcomes that AMPC are looking for as an industry association, as the Australian Renewable Energy outcomes also for the decarbonization of Australia, and end up impacting Australia as well as a nation, right? So even though it seems to be just one project, it also represents a seed on how Australia can move forward into a much more sustainable way of doing business in general. So in terms of drivers, we have a combination of 3 different entities, right? Starting from the processor, that they needed to, of course, ensure robust environmental compliance, but also look at generating additional income through recovering bioresources, establish a reputation as a leader in sustainable practices in the sector, and Bindari is really committed to that from our experience working with them. Also boost energy independence, meaning they can produce partially of their own energy from renewable sources on site. And also very particular to this plant is enhancing the reliability of cost efficiency by producing the self-supplied food grade bio CO2. And I'm not sure if everybody is aware of that, but the price and the availability of food grade CO2 in Australia has been critical for operations. There is limited supply and the prices, they went up a lot. So there are several producers looking at recovering CO2 from either from the flue gas or from their biogas. In regards to AMPC, there is a program and there are KPIs in regards to establishing a bioresource recovery precinct. So AMPC has been very supportive of the facilities wanting to walk that path. And that links to some other projects that I'm going to mention later to you. And then the AMPC has also as a KPI that 30% of the red meat processing industry is powered by renewable energy. They also want to have 5 piloted clean alternatives to fossil fuels for process heat into the processing plants. They want to transform byproducts into value and drive sustainable innovation through circular economy and decarbonization. And of course, ensure that cost savings and efficient processes, meaning we are not only talking here about the environmental side of sustainability, but we're also talking about the financial, how things stack up financially for the processor and for the industry overall. And in regards to ARENA, of course, this project supports the global transition to net zero emissions by accelerating pre-commercial innovation. So meaning this kind of process, even though they are well implemented in Europe, they are not yet a common practice in Australia. ARENA also wants to improve the competitiveness of supply of renewable energy, or minimizing costs or optimizing costs for the use of renewable energy, promote the uptake of energy efficiency and electrification. In this case here is by adopting anaerobic practices into the management of waste, so you reduce your overall energy consumption in your operations, right? And obviously share knowledge to support innovation. So that's exactly what we are doing right now. We are here sharing our findings to the industry and to try to people to be more aware of what is possible. So the bioresource recovery concept, we started to develop this together with AMPC probably now 5 to 6 years ago. And the idea was really to maximize the use of everything that comes out of a red meat processing plant. So in the beginning, we were really looking at the water recycling side of things, on how to produce the higher quality water that we could use for non-contact applications in the processing plant. And from that, we started to evolve into more sophisticated concept where, yes, you produce the very high quality recycled water using innovative combination of biological nutrient removal, membrane processes, and multi-barrier disinfection. And the focus here is really to maximize the recovery of high quality water. It's not only environmental compliance, only just a little bit of nutrient removal, but this is really high quality water. And by doing that, we concentrate all the streams that are high energy productive, high carbon content, like the sludges, the fats and oils, and the protein, everything that can be used to produce biogas. They are concentrated in the form of a sludge, and then they are processed in a separate reactor type of anaerobic digestion. So just to make very clear from beginning here, this is not a conventional covered aerated lagoon process or anaerobic lagoon process. This is different. So we treat the wastewater in a way of water recovery, and then we process the high energy value substrates together into an anaerobic digester, a CSTR kind of digester. We combine the sludges with the solid materials that are produced as a byproduct in the processing plant. And that can include conch, manure, fats, oil and grease, gut contents, undigested feed, and other organic waste as part of a combined co-digestion substrate material. We are also, as a side project, assessing, along with AMPC and RACE, the optimization of that process on how can we enhance even more the production of biogas by combining this the red meat processing byproducts with external substrates such as grain waste, food waste, and other things. So that's a stream of work that is happening parallel to this, and there is a lot to say about that. But we are today focused on this project here, right? From the anaerobic digestion, yes, that is everybody knows about this project. You can produce biogas from it and recover energy and heat, but we are trying also to maximize the outcomes of the biogas plant, and not only putting a CHP engine and producing electricity and heat, but improving the quality of the biogas by further treating the biogas to produce biomethane that can be used for energy production, or in the other stream would be to use the biogas in the CHP engine and recover the CO2 from the exhaust, which is what we did for this project. So doing that, you really maximize the return on investment because you add the value to the byproducts. So the CO2 that would be just burned and be released to the atmosphere, in this case here, it will be processed and captured and processed to become a valuable income source for the processing plant. In regards to the digestate, which is what is left after you digest everything, is like a liquid slurry. And in many cases, that's been the showstopper for implementing digestion, anaerobic digestion in Australia. It's being how you dispose the digestate, and the environmental regulator can be very strict, especially here in Western Australia. You basically, is really almost a showstopper for going forward. So we also developed a project called bio-based fertilizers, and we are now into a market research stage of that project. So we are really going deep into how we can produce a commercial valuable fertilizer based on the digestate. So we are working several fronts here. One is unlocking and maximizing water recycling in the plants that AMPC is working with a separate consultant. We are maximizing here the value of the biogas and CO2 recovery and the biofertilizer. So the idea is that all these things here become financially attractive, either for the processor itself or for an external investor that could offer an alternative business model for build, own, and operate these kind of things and provide the service to the processors. So this work is being recognized nationally in Australia. We won the Australian Water Association Research and Development Awards last year for this work. It's being published also in the International Water Association Anaerobic Digestion Conference that happened in June earlier this year. So we are getting lots of recognition from the industry from this project, and we are really excited to see the support from both AMPC and ARENA into implementing this in real scale here in Australia. So let me talk a little bit more in detail here about the methodology. So we first started with the wastewater treatment plant design, which is the beginning of everything. So this concept is not that you do one thing and not do the other, it's everything integrated. That's where you recover the maximum value, right? So everything we did in the wastewater treatment was we use Excel calculations and BioE modeling to verify and also to test the robustness of the process. So we know how can we respond to fluctuations and how can we produce very reliable, high quality treated water for the environment and for irrigation and for process as well. So we have quite a good assurance on that. In that stage, we had a two-stage peer review done by external consultants, one consultant from Australia based in Melbourne, and a second one in Austria, where they are very familiar with the red meat industry. So everything we did was checked and tested, and we are very confident that what we put out there is really, really robust. Okay. And then we did the organic byproducts characterization and quantification, meaning we collected samples from the processing plant in Inverell, and we sent out to a laboratory to test the biomethane potential and also the characteristics like volatile solids and total solids. That gives us an idea on how that those materials perform in terms of producing methane. And also we did a combined sample, not only the individual materials, but simulating the real final co-digestate sample. So that was a very extensive process to get those results done and analyzed and converted into how much energy we can really recover from that. So from there, we calculated the biogas plant, and that was also tested against real cases in Europe. I had been 3 times in Europe for visits to similar plants. The first time in 2018, and then 2022, and then again this year. So we keep track on what's happening there and how what we are developing here compares to what's happening in Europe, right? So we are quite sure that there is not big differences, and that's something I hear a lot from clients. Oh yeah, that works in Europe, but in Australia nobody has done it. So I can tell you guys that the weights are very similar. Cows are cows here and in Europe as well. They're not different. Oh, and then we moved into the CO2 recovery plant. We had the subcontractor to help us on the design and choosing technology here, which was EVA Technologies based in Queensland. So they were very helpful to help us into comparing technologies and with their practical experience on that area, right? And we end up with a very lean design for capturing and maximizing the recovery of food grade CO2. From there, we went into the design of the biofertilizer plant, and that was also based on a 2-year study where we assessed many different ways of increasing the value of digestate. And we do have a PhD student still at the moment working on that at the University of Western Australia, really focused on how can we optimize the conversion of the digestate into a fertilizer. So having all these processes designed, so water, biogas, CO2 recover, biofertilizer, we went through a phase of cost estimate. And this was not just a desktop cost estimate. We did actually get quotations from suppliers. I went to IFAT in Europe, to the big technology fair, to meet suppliers and to establish relationship directly with the European suppliers. So we are also quite confident that not only the processes we designed, but also the costing that we put forward as CapEx is very robust in terms of updated from May, June this year. And while after we had all this, we had an economic analysis done where we consider all the potential revenues that come out from this project compared to costs and operational costs, and we put that on time. So I'm going to present all these results in the upcoming slides here. For the facility that we are using as a case study, we assume the production capacity of just over 135,000 tons of hot standard carcass weight, and that was the starting point, right? I'm going to come into a little bit in more detail. So the idea is to implement the project in 2 stages. That would be stage 1 and stage 2. The stage 1 would be around 67,600 tons per year. And I'm not sure if everybody is really aware of what that means, right? It's not only per head of cattle, but it's how much hot standard carcass weight production it is. So we standardize the yield from red meat processors based on that number, right? So just for you to have a comparison, the Australian processing plants are divided between micro, small, medium, and large. So for a processing plant to be considered large, it has to process above 40,000 tons of hot standard carcass weight of beef. This is for beef numbers, right? So this is already a large facility, considered a large facility in the Australian context. And once it achieves the ultimate capacity, it's going to be on the top, I would say the top 10 facilities. So it's not a small, tiny processing plant. The other thing I want to show is that what we are proposing here is a large, it requires a large footprint because we have very high retention times on the digesters. It can be up to 60 days. So once you put the material there to recover biogas, average would be 35 to 40 days, but depending on how much biogas you want to recover, this can be even more, can be 60 days. And in some places in Europe, they are operating with 60 days. So if you compare the size of the processing plant and the size of the resource recovery facility, it is kind of almost the same size, right? So it's a very significant project. And in this case here, we would need around 2.6 hectares to implement all the 2 stages of the project. Just a little bit more in terms of the red meat industry distribution, just for you guys to understand where we are situated here. And I'm just already giving the heads up that I'll present all the results for the large capacity, but in the end, I'm doing an assessment on how these things stack up for smaller producers and what's the kind of sweet spot where you should start thinking of doing something like this. So around 912 heads of beef per day is equivalent of around 40,000 tons of horse and carcass weight. So you can have an idea of sizes, right? Okay, so I'll start talking a little bit in more detail about each of the steps and how we got there. So the first one is the water recovery plant, that we don't call it wastewater treatment, because really the objective here is to recover high quality water that can eventually be used in most of the processing applications, of course, non-content applications in the process. So we start with a very robust pre-treatment using an organic coagulant. And the reason why we do that is to maximize the recovery of all the contents that are high energy value, like the lipids, proteins, fats, and everything. So we are really focusing on having a really good pretreatment, and using an organic coagulant is something we are also testing as a AMPC project, but the idea is to eliminate metals from the process from beginning. So when you get all the way to the end on the biofertilizer application, you don't have any limitations in terms of having heavy metals and contamination with aluminum or other things that can come along with metallic coagulants. So this is one part of the innovation, is focusing on that step. And some plants, they say, no, we don't do the pretreatment because we want to create the crust. So in this case here, we don't talk about crust. We want the crust out of it, and we want that in the digester to produce biogas, okay? And then we follow via 3-stage biological nutrient removal. And that is because we really want to go through maximizing the removal of nitrogen as the main culprit here, but also phosphorus. So we design the system not relying fully into chemical removal of phosphorus. We are including a step where a good part of more than 50% of the phosphorus is already removed in biological treatment. That will reduce capex, that will reduce energy consumption as well in the further steps, and the need for chemicals in the site, right? And also you lock the phosphorus into the biomass that ends up in the biofertilizer as well. So that's another benefit there. We also are proposing the use of ceramic membranes as a tertiary treatment, and that is moving out from the conventional polymeric membranes that are really outdated. I don't know how we are still using them in Australia, but if you go to Middle East and Europe, they're all being replaced by ceramic membranes. And that is because of the robustness in the cleaning of the membranes. They have a much longer life, and you can also use high pH, low pH. There is no limitations in terms of chemicals and damage in the membrane that you have compared to polymeric. So we had a really extensive research on that, and that is the option we are putting forward here. And then, of course, we follow that with a double barrier disinfection, which means we are using ultraviolet in a very high log of pathogen removal, followed by chlorination, just enough to keep the wastewater safe for distribution, or the treated water safe for distribution. We are also at the moment exploring on the side a little bit of advanced oxidation techniques to improve the reliability for recycling, and that would be to destroy any residual of chemicals like pesticides or antibiotics or medicines that can potentially end up in the water, which is not supposed to, but it could happen. We actually tested the wastewater for pesticides and for antibiotics and medicines. We could not find anything on this scope, but we are still considering that on the side as one more step of safety for the future recycling. So in this case here, we are producing Class A water produced for in-plant recycling and irrigation, and just making it clear, the in-plant is not non-contact processes, that nothing touching the meat, right? It's just cleaning applications and maybe boilers or cooling towers and all these kind of things. So, well, in the case of Bindery, they use skim water. So when we do the feasibility studies, there is a price they pay for water, and then of course this can offset the cost. Some other processors are luckier that they have bore water and they don't need to pay for a water bill. However, we are aware that across Australia there is a water reform, and the water allocations are going to become a lot stricter, and the cost of water is going to start increasing. And also the amount of water that people can remove from the ground is going to be decreased across the board. So after the wastewater treatment plant is, yeah, that's the process that I'm telling. All the sludges and the solid wastes are directed to the biogas and bio-CO2 plant. So I'm just putting here is an aerial photo of a similar facility in Germany, and I was there just in May this year. And here it's quite interesting because you can see it's a combination of different things. You have the red meat processor. I don't know if you can see on the left top here. That's where they have the little processing. I think they're dairy in this case here. They have a huge solar farm, if you can see in the middle left here. And then they have the biogas plant. You can see the digesters here. And then more recently they implemented now the CO2 recovery as well. So these cylinders here are the CO2 recovery. So it's quite interesting to see that is not out. The solar is better than biogas and vice versa. So the biogas in this case can be used as a battery to the solar. So when you don't have solar energy produced, you can burn biogas and produce energy from there and balance the peaks and using that combination, which I think is really ideal for, especially if you have land available, if you are not in the urban area, right? So the thing we designed here for the biogas and bio-CO2 is a pre-treatment where you have liquids and solids mixed and conditioning. And the conditioning can be pasteurizing by using heat. And we are also assessing now under another project the possibility of chemical conditioning with potassium hydroxide and other ideas. Maybe also zeolites to make sure that the dewatering process is more straightforward. And also you can capture more nitrogen from the digestate. So each line I talk about here is an entire project that we are developing separate and in very deep level. In collaboration with universities also, so it's not everything done here in my office. We do have University of Western Australia, we have Griffith University, we have partners that are working very close to us to develop this. And then the anaerobic digestion reactors themselves, so they are fully mixed reactors and they are maintained at 37 degrees to improve the digestion process and making sure the bacteria is all happy there, right? And some people ask me, why don't you go mesophilic, which is or thermophilic, which is a little bit higher temperature? And the issue here with red meat industry substrates is it can be ammonia inhibition. So when you go much warmer than thermophilic, you might have issues with the ammonia toxicity inhibiting the process. So we also did that extensive research in Europe to decide what's the temperature and how we're going to go about it. And we did test also in bench scale across the early stages of the project to define that. And the other reason why is then you lose less energy, right, by heating the temperature difference for those huge reactors. For the energy recovery, in this project, we are using CHP engines. And from there, you can recover thermal energy and electrical energy. The thermal energy can be partially used to warm up the reactors, and the other portion goes to the biofertilizer plant to dry the digestate. So I'll talk about that in the next slides. After that, we have the CO2 recovery, which is a bio CO2 recovery. In this case, it's going to be post-combustion. We decided to go post-combustion because you can recover more CO2 at that stage. Pre-combustion is when you focus on recovering a more pure biogas. Let's say if you want to inject it in the grid, mixed with the natural gas. But for this particular case here, the focus was in maximizing the recovery of CO2. So it's post-combustion. And then it goes to post-processing of the digestate, where we have a solid leak separation steps for the digestate that go into the biofertilizer plant. So there is an entire world here in all these steps, including what you do with the liquid from the digestate, and if you can further recover nutrients from that, or you can incorporate that into your wastewater treatment plant. And there is many avenues you can explore there. Always very complex. So for the case of Pindari, we had a variety of substrates that were available, and that will be available also in the future with the new wastewater treatment plant. So a big part of it is the secondary DAF sludge from the upcoming wastewater treatment plant. So because we have the biological nutrient removal plant that's going to be installed and operated, we are going to produce nutrient-rich sludge from there. And then we have a combination from different types of byproducts from the plant, manure, a few other solid byproducts from the processing plant, and also crop stubble from the farms that Pindari has surrounding the processing plant. So it's not that we are using bioenergy crops themselves, we are just using whatever is left on the fields after they harvest the corn as a substrate as well. So there is a good matrix there of combination of substrates. It's good also because you don't rely only on one. If something happens that suddenly something has a bigger value on the market or something. So it's a mix. We did the individual biomethane potential analysis, but also a co-digested analysis. And what we got as an outcome is that we can produce around 8 million nano cubic meters of methane per year. It's a lot of gas there, which is awesome. From that gas, we can recover about 183 gigajoules per year of energy, while you have 2.3 megawatts electricity and 2.4 megawatts thermal. So it's quite interesting and attractive from the energy point of view. And in regards to the CO2, we decided to go by the amine process, which is, in this case, we have a better economic feasibility for this case of plant. So we have several reasons for here, but the cost for a metric ton recovered is around between 150 and 220 when we implemented this system. And if you're going to buy the food grade CO2 in the market, if you can ever find it, actually, you can pay up to 2,000 or even more. I'll be even curious to hear later if anybody had an experience with that, how much they're paying for CO2 at the moment, right? So at the same time, you also need the skilled technicians, the plant operators. It's not a plant that you can just leave it there and run, but it gives you a really good return on investment, as you're going to say later. This image here was sent by Ivo after our trip to Europe, so thanks Trevor for that. Okay, so after we recover energy, heat, and CO2, we move on to the biofertilizer plant. That's where you receive the digestate from the anaerobic digester. So we are estimating that we are going to receive around 100,000 tons per year of digestate at 5% total solids. And that is based both on the assessment we did on bench scale BMP tests, but also the experience we had in Europe. So we saw similar facilities operating with similar substrates, so how the digestate end up. And then we also have the analysis and the quality of the digestate in terms of nitrogen, phosphorus, total solids, organic matter. So it's already starting to see it from a fertilizer point of view, right? So the first thing we do with the digestate is the watering to around 22% solids. That is normally done with using a centrifuge, and we need a bit of polymer there to make it thicker and the watering a bit easier. Interesting enough, we have a PhD student working only on that step of the process in optimizing the digestate. The watering is a very critical step of the project because you can separate the water from the solids and then handle the solids in a much smaller scale, right? Because if you want to get into thermal drying with a high content of water, then you're going to use all your energy for that. So after you dry your cake to around 85% total solids, you get into the pelletizing production. There you can go up to around 90% total solids, even more if you want to. And in this stage here of the pellets production, you can actually top up the pellets with different types of micronutrients. If you want to increase, let's say, potassium or selenium or some specific crop that you want to do, we can tailor that that final product to suit the market. And at the moment, we are also developing a parallel project with AMPC and Rich Grow here in Western Australia to really maximize the value of that product. So we are really excited with the outcomes. We are heading to the finalizing the project in the next 2 months. It's becoming really attractive from the financial point of view. So when you look at the whole outcomes you have from the project, it's quite exciting that everything has a market and has a value. And before they were just actually an issue, right, a problem. And then after, besides the pellets, you have the liquid filtrate that's going to be around 96 tons a year or cubic meters a year. That is going to, in this case for Bindari, we have designed for this to return to the wastewater treatment plant. But we might look at different solutions for that in future, like recovering struvite or maximizing the recovery of nitrogen from there as fertilizer as well. Okay, so in terms of process, that's where we are. And the bio-based fertilizer is a little bit of a gray area in terms of regulation. That's an important thing to touch base about. There is nothing written in New South Wales or in Australia, actually, in terms of regulation to using a biofertilizer based on the red meat digestate. We used the biosolids guidelines as a comparison on how we could really make this possible. So we are actually, if there is anybody from the regulator there, I think it's about time we start thinking of putting some regulations around that and how can we enable this to become a product and not treated as a waste, right? So in New South Wales is one case. In Queensland, they have the end of waste code, which is also a really lengthy process to get there, but it's possible. Western Australia, it's seen as a case by case. So it would be really nice to have a national initiative on valuing the bio-based fertilizers from the meat industry, right? And interesting enough also is that because this is not coming from domestic waste, not FOGO, not domestic, it's coming from industry. We have control on contamination issues. For example, nobody's going to throw a battery in this kind of process here. It's all controlled. Nobody's going to throw glass in it. So there is a much higher quality on what we aim to produce in a red meat processing plant. So to decide which process we went through to create the biofertilizer, we assessed different ones. We assessed the production of biochar using pyrolysis and gasification and the different options, right? So we had a multi-criteria assessment to get to the pelletizing as we got. In the beginning, I was actually really passionate about biochar. I was thinking, oh, that's the ultimate solution. But when we started to test the market during the project we did the AMPC about the bio-based fertilizer, we understood that most of the consumers, they were interested on the soil amendment capacity of if you maintain the organic matter in the pellets, so you can retain more water, you can improve the soil quality and input nutrients. When you go to biochar, there are other benefits from that in terms of surface area and slow release of fertilizers. But when you compare the costs and the market needs, we found out that pelletizing is the most valuable cost-benefit solution for this. So this photograph here is more or less how that's going to look like. It might look a little bit different if we add extra sources of potassium, might be a bit whitish. The idea is to be odorless as well, minimize the odor by the way we pasteurize it, and perhaps adding zeolite as well to make it really like a commercial product. So now I think everybody's thinking how much this is going to cost. This woman is talking about all these things, right? So what we did for Bindery, we assessed many scenarios for the case. We just designed for 2 stages, and then we thought about, okay, what if we do everything in a full scale at once, meaning the wastewater treatment plant, the biogas plant, the CO2 recovery plant, and the biofertilizer plant. Then the second scenario, we didn't do the CO2 plant. The third scenario, we thought, okay, we're just doing the wastewater treatment, forget about everything else. That would be like business as usual, right? Let's just get rid of our wastes and not look at it. And then scenario 4 would be not doing the biofertilizer, do everything else, but then in 2 stages. In scenario 5, no CO2. Scenario 6 is similar to scenario 1, but then done in 2 stages. Implement half now, half a bit later. And scenario 7, it's the same as the 6, but without the CO2 plant. So we compare all this and how the return on investment and CapEx, OpEx would stack up. It was a really brilliant work that Leticia and Lucas did together here, and it was fun. We had promised 3 scenarios only, but then we end up a little bit beyond, but it was interesting. So these are the numbers. We realized that the scenario 1, implementing everything, and scenario 6, implementing everything in 2 stages, were the most favorable. So if we implement everything at once and you have the capacity and the byproducts to produce it, you need around $60 million as a capex to implement it. You know, give or take, depending on the market at the moment to make a decision. But about 40% of this cost is into the biogas plant. That's the most expensive part of it, and that includes the CHP engines. So that there are very considerable investment in there. And about 30% of the investment is the wastewater, the water recovery plant, and 20% the CO2 recovery plant, and 14% the biofertilizer plant. Funny enough, the last 2, the CO2 recovery and the biofertilizer plant, they are the smaller investment, but they are the biggest return. So you're going to see later, they are really critical to make these things stack up financially. The other scenario we split in 2 stages. And imagine that we are going to do all the earthworks up front and have the site preparation ready for like a drainage, lighting, everything in the stage 1. And then just implement equipment in stage 2. So you would split the 2 a little bit. So it gets a little bit more expensive and around about $1 million more in general. So depending on the production capacity, the recommendation would be to be in 1 or 2 stages. That's going to be up to the financial people at Bindery to decide how they want to go about it. So in regards to the economic analysis, the revenue from everything we have, right? So the way we calculated the expected revenue in water for Bindery was replacing the portion of the city water that they're using in their facility with recycled water, which means it's not the full water produced, it's just the amount of water they are able to use as recycling. So it's about, I forgot how much it is now, but around 20%, I think, of the total water. And then the other part is going to go for irrigation of the crops there. And then we have the electricity and thermal energy in the plant. And so the revenue will be around $1.2 million a year from electricity and 400,000 in thermal. And the liquid CO2, we would be able to recover around 3,000 tons of CO2 a year. And that's interesting, important to mention here that this is matching to the demand that Bindery has at the moment. So we can produce more than that, but we only use for the economic assessment, replacing the cost they have with self-produced, right? So the potential here can be even bigger if they can sell that CO2, for example. So the revenue from that would be around $3.2 million a year alone, just the CO2. And then the biofertilizer, around 3,000 to 2,800 tons a year with a revenue of $1.7 million a year. For what we are seeing in the more recent work we are doing now in the market assessment, that can be better, can be more attractive. They were talking today when we met with UWA around $20 to $25 per ton, so that would be a lot more than this. And then there is a bit of a savings on disposal. So things that are potentially going to disposal on land. And so in the case of Bindery, is really basically the transport cost because they have their own land composting facilities at the moment. So this can also be different if you are paying for landfill fees and longer distance transport. So as you can see, there is a lot of revenue that you can get from that. And then you can also obtain carbon credits from all this exercise, which is quite exciting. So if you compare all the scenarios that we have here, you have the scenario 1, which means implementing everything now, but that is also assuming that you have all the substrates to feed the plant, which is not really the case, right? So as if they are already producing the 135,000 tons a year now. Scenario 6 is when you do that in 2 stages. So these are very attractive. And scenario 3 is if you only implement the wastewater treatment plant with no recovery of biogas or biofertilizer or nothing. So you can see they're all, almost all positive except for the only wastewater treatment plant. There is a good return on investment. There is, of course, a payback time is around 7 years. It's not tomorrow. Like, it's not. When you look at these investments, you need to think that you are moving from a pure liability on managing wastes, right? That's the old linear thinking, into recovering value from byproducts. So we cannot expect the commercial payback times of 2-3 years as investors look at. This is an environmental and economical outcome that has to be achieved together, right? So 7 years time is quite attractive, thinking that the comparison would be just lost, right? So this in summary, right? We designed the wastewater treatment plant to treat 919,800 kiloliters a year. The solid streams produce around 8 million normal cubic meters of biogas, 2.3 kilowatt hour of electricity, 2.4 kilowatt hour of thermal, which is combined 1.4 gigajoules per ton of hot sonic carcass weight processed. A CO2 recovery potential of 9,200. So if you see, remember before we were talking about 2,900 and combined would be like 5,000, 6,000. So you still have a surplus here of around 3,000 tons of CO2 that could go to the market if you can find a buyer in the area, right? And then plus about 5,000 tons a year of fertilizer pellets. So there is a lot of good outcomes there. Basically here, nothing is going to waste, right? It's really incredible. It's super good. So as I promised before, I said, okay, this is big. I have a smaller processing plant, how that would look like for me. And then with AMPC, we developed another project called the Bioresource Recovery Centers. And for that project, we used the information from Bindery and also from another processing plant in Western Australia, which is a different capacity and processes lamb and beef together, not only beef. So there are two different capacities. And plus, we had information from 7 other processing plants around Australia from the Digital 2 project, which is before. So we managed to simulate how that would look like for different capacities and different kind of materials coming in. So we realized here that more or less the medium-sized capacity facilities, which is around 40,000 tons, that would be more feasible. You have a bigger payback time and a shorter a shorter payback time and a bigger revenue. But if you see here, even smaller facilities, even though it might take almost 20 years to recover the money, they don't go on the red, right? They still can make it feasible, even though there's not a big, incredible return on investment. It's at least break even in the end of, I don't know, 18 years or something. So this is quite interesting, I think. However, this is considering that you implement the entire system, right? With CO2 recovery, with fertilizer, with everything. So you can see in this graphic here on the right that the food grade bio CO2 is a big portion of this revenue. So what I say is that we really need to assess everything case by case. Some places, for example, the recycled water might be more significant if they are paying the commercial rates, like $4 or $5 a kiloliter for water. This thing can change completely. So this is the footprint based on bindery. And I think each different processing plant will have their own footprint on what is the most valuable resource on their area, right? So we are working with AMPC now into moving to use all this knowledge and information we had to update the digital tool. And I don't know if everybody's aware, but the digital tool is a tool that we have online from AMPC, where you input your production capacity and you get all the outcomes from energy, water, bio CO2, and biogas that you could obtain. Unfortunately, the model is really out of date now because it was pre-COVID, so the costs are different, the energy costs are different. So we are looking at updating it now. So I think from the bindery project is it. I'm just conscious of time here also. I know I have another 7 minutes to wrap up. So I'm just going to quickly go through the European technical tour, which is, it was funded by AMPC earlier this year with the objective for me to explore. The main focus for this trip this year was into the biogas upgrading schemes. So how they are recovering CO2 and upgrading biogas from different types of waste. So this photo here is the same one I showed before from the aerial photo. So they produce a lot of biogas here from mixed dairy waste and crops, and they recover around 1,000 tons a day of liquid CO2 from this facility. It's the biggest biodigestion plant in Germany. So you can see, you drive around there and you see. So the big domes here are the biodigesters, and here on the left, these towers here are the CO2 production facilities. Okay, and besides doing these site visits that were actually organized by Evo Technologies, I also spent a couple of days at IFAT in Munich talking to lots of suppliers. So it is a huge fair. You really need 4 days to go through it if you are very organized, because it's really easy to get lost there. So just the highlights there is a huge focus on biogas upgrade and CO2 capture. And there is some interesting things in terms of advanced wastewater treatment, especially to get nitrogen in very low levels. A few things I saw there that are interesting to bring to Australia. Some technologies on increasing the biogas desulfurization, which is very important when you want to inject it on the grid and prevent corrosion in the end users, right? There was a few interesting things about biochar production and sludge treatment on how to use pyrolysis and smaller scale systems as well for recovering energy from that. Also some interesting pelleting and packaging, because now as we move into producing a biofertilizer, it's not only about that, you have to sell it. So there is a lot of marketing and other things in the end of the chain there, right? And then renewable resource utilization, so how to upgrade biomethane and liquefying CO2 for market use. Lots of interesting conversations. It was really, really cool to spend time there. So yeah, we had, I'm just going to wrap up, I'm not going to go too far. So we visited many plants. We saw you can see the combination of older biodigesters in the back, and then the more modern CO2 recovery plants. they are popping everywhere. So you can see that it is not anymore an optional in Europe. It's everybody's doing it. It's just normal, right? And here, this one I found it really interesting because it was a small family farm with a small digester just for the dairy farm, but then they had the CO2 recovery here in the middle, just for a small. So it's not a meaning that it has to be huge scale. That can be a bit smaller scale as well. And this is a CO2 recovery plant it's going to be from an abattoir as well, mixed with crops like a co-digestion, similar to what we are looking at implementing at Binduri. And they were still under construction, so it was quite interesting to walk around while they are still installing things and everything brand new and shiny, really cool. And understanding how the owner was so excited to see this implemented. And the last thing I want to share is that turning risks into opportunities, right? It can be scary to do all these new things and jump, but when you are in capable hands and you know what you're doing, it can be really exciting. And I'll be really looking forward to help and assist moving forward. I think that's what I had to say for this hour, and happy to take any questions now.
Thanks, Fabiana. That was a really good presentation. A lot of detail in there.
Thank you.
A lot to think about. Chris is joining us for the Q&A now. We've had a couple of questions and just some comments that I have. I mean, you had some great illustrations there around the breakup of substrates and co-substrates in terms of potential, bioenergy value, and then the integrated approach and your staged approach, and the time frame and the scale of the investment is significant. But you can see that some of those stages have significant revenue as well, particularly in the bioresource areas. And interesting to note that the wastewater treatment only doesn't have any revenue and is not paying for itself.
No.
So one of the ways
and also it would increase the carbon footprint, right, to achieve the quality of water.
Yeah. So we've got a couple of questions there. So I'll go through the ones that I noted. The first question is probably for Chris. And it was around Binduri's comments on the project and what might be your next steps.
Off mute. Everyone here?
Yep.
I think next steps for this is, it's a multi-tiered approach. The project, to Fabiana's comments, has lasted a number of years now, and it really is almost an ethos shift for the red meat industry if we would go down this path. It's not just talking about how do we deal with our waste, it's really how do we become part of the circular economy, and it has so many other considerations apart from just an Excel spreadsheet that spits out an ROI. I think the FID stage, will be very, very complex, but the amount of interest, that this webinar's brought, the ARENA funding's been just fantastic, and the amount of industry interest, outside finance interest, I think it's a real way forward for the red meat industry, and certainly Binduri, take that risk and make that plunge. But as far as the next steps, it's certainly rounding out the reporting with Fabiana, sharing it amongst the industry, some of our partners, and then really diving into that ROI discussion, the FID, and working out where it fits into our future as good corporate citizens, and how we can turn the waste problem into a revenue stream potentially.
Yep, and kudos for Binduri and ARENA for getting on this together and making the work happen, Chris. So you mentioned the final investment decision, obviously important and not straightforward. And I might go to Fabiana for that question. Is what work would be involved in a final investment decision? What further work is needed to ameliorate perhaps the upfront cost, a staged approach with co-investors, any of those sort of things to help a final investment decision, whether some of those solutions in Europe maybe you saw?
Yeah, the number one thing is we built in a lot of safety on the design of what we did. Everything has about 60% safety, like a robustness, because we really wanted to make sure we are not being skimpy on that. But we want now to value engineer everything. For example, the duplication and the staging of the project. We at the moment are in a level where the level of reliability of the plant is 99.99%, so it never stops. You have installed equipment, redundancies, everything in the plant. So it is really working with Bindery to understand how active the maintenance team is in terms, can we have spare pumps sitting in the storage instead of installed? Do we really need to have the redundancies in the plant? Can we bring down the 60% into 30% maybe reliability? And how many days can you afford having this shut down, you know, in case you need to replace an equipment? So there is a value engineering there that I believe we can reduce capex a little bit. And then there is also the way we stage the implementation and how we work with suppliers. For example, the CO2 suppliers in Europe, they were renting the equipment for the first 2 years. So they wait until you break even and then you start paying. So it's really developing those relationships directly with the European suppliers to leverage on those kind of benefits where you don't need to cash up all your $12 million in the first day. They come here, they install the plant for you, you sign a lease agreement, and then you start paying in 2 years when you start benefiting from the revenue. So it's a combination, I think, of value engineering, staging, and business model as well. Maybe also find partners in the operation, because this is not core business for the red meat processing industry. So in the case of there is another case we are working right now that we are finding a specialized company that only operate these kind of systems to be a partner on delivering. That can bring also efficiencies in terms of resources, human resources, right, and reduce capex. So there is a few things we can do to make it more feasible.
And Fabiana, are we seeing any of those co-investors here in Australia at the moment that are willing? I mean, one of the things that you brought out here in terms of the scale of the investment and the return is that it is investable to those large type investors. Are we seeing any of those sort of express interest in these integrated large projects?
Yes, there is, but there are two types of investors. There are the types that want to come into this because of the renewable energy, and they want to have a energy selling agreement, and then the water is the collateral, and that can become a little bit expensive because that's not their core business. They're the people that are normally working with solar panels, with simpler systems. And we figured out that was a little bit not financially attractive, but there is also purely financial investors where they have cash and they need to develop a portfolio in green projects, in carbon neutrality and all these things we are doing. So there is money in the market for this kind of investment that I believe it could be more attractive financially for the processors.
Chris, just picking up on what Fabiana was talking about, in terms of the feed study, has it helped you with more confidence looking at an integrated approach with that very first bit that doesn't give you a return on investment but is compliance based, and is the wastewater treatment? Does it give you more confidence to do that correctly, and so that maybe that can be ultimately integrated with the bioresource recovery?
Yeah, I think they go hand in hand. To Fabiana's point, you can't have the return, which is the smallest part of the investment, without going to that level of wastewater treatment. And I mean, even through the process, working so closely with Fabiana and paying so much attention to the potential in our wastewater, we've already made improvements just by focusing on efficiency of DAF processes and filtration and screening and stuff like that. So it's been valuable in itself, which now enables us to sort of take that master plan approach rather than having to have knee-jerk reactions to a compliance-based problem, rather than being able to focus on what we want to do to set up for the future.
That's great. I like that. The master plan for integrated wastewater treatment is certainly novel, I would have thought, including those later stages. Yeah. So any idea or next steps when your wastewater treatment work might start? I guess there's final investment decision to make and a master plan before you go to that
Yeah.
Is that the
I mean,
idea?
judging by progress and you know the amount of things that we would need to work through, you know, partnering with Fabiana, if we continued, you know, there's probably at least another 12 months of, you know, industry talks, regulator talks, value engineering, all of that kind of stuff before I think we'd be even close to an FID. To be open and honest, I mean, there's a lot of moving parts. But that's kind of what our plan would be for the next 12 months to back up and you know make value out of this project. And I think talking to other people in the industry as well, you know, you can see there's a number of other red meat people on the call today. I think, you know, joining together as an industry, working with AMPC, I think that's where we get the leverage to make this a reality, you know, for our industry. We've all got similar waste profiles, we've all got similar energy profiles. You know, I think if you're going as an industry to Europe or to Australian suppliers even and showing there is a market base here in Australia, you know, that's where we get you're going from a novel high risk engineering solution that costs everyone to, you know, slowly de-risking that into knowing technology, known process. The more industry sharing, the more knowledge you have, the more data you get, you know, that's where you make the value engineering worthwhile.
Thanks, Chris. There were some other questions there. I'll probably read them. One was asking 3.2 million from 2,906 tonnes of food grade CO2 is $1,100 a tonne gross. Is that correct?
Chris, you can reply that question for me.
Is your spreadsheet, Fabiana?
No, we don't want to disclose the numbers, but yeah, if you can.
For context, that is an average number over a period of time for our production, but it is representative. I think anyone who buys liquid CO2 in the quantities that we do have all experienced the force majeures recently. You know, there's numbers that were higher than that, and there's you know, a normal contracted number that's lower than that, but that's a fairly representative number, including some escalation for what we see happening in the future. Happy to hear comments for anyone else on the call that purchases CO2. I mean, it's we're all playing in the same market. The numbers are all fairly similar.
Yeah, that expense as well as the lack of reliability, I think, is a problem as well in terms of supply and the price. There's no consistent price, but yes, it is expensive at those levels. That's a gross figure, by the way. Whoever asked that, it's not what you revenue you might get from selling it. There were some questions around carbon credits, other forms of funding in Australia for this, certificate type schemes. Did we cover that? We did on the biogas, I think.
Yeah, we did. We did an overall assessment in carbon credits here. One is by displacing the use of coal as an energy source, right, into renewable energy. So that's one source of carbon credits there. And then when we produce the bio-based fertilizer, whoever is going to use it, if it's going to be bindery on their own fields or if it's going to be external, then there is a question there, we don't know. So you have also replacing chemical fertilizer with the bio-based fertilizer, so you don't have the whole carbon into the fertilizer. And the transport costs for the CO2 from outside into the plant. So there is a few items there that we can leverage for obtaining carbon credits and increase the profitability of the project there.
Thanks, Fabiana. There's another one there. You mentioned, Fabiana, during your presentation around biofertilizers and the regulations that are around digestate and how you apply them, and being different regulations between different states. Is there an example in the EU that you really liked? Are there any case studies out of just the digestate application, perhaps, that we could learn from?
No, the EU actually is very permissive into using irrigation with digestate. So you drive on Bavaria and it's a bit smelly. They really use as an irrigation fertilizer. So only now in Netherlands and France, they are starting to limit that, and they are starting to have to move into the biofertilizer side of things. So yeah, I think we're going to have to walk together with Europe on that part.
Yes. We don't have any more questions, do we? Unless Letitia or you can see any other questions.
There was
Lauren.
one there from Christy Burke, I think for Fabiana, about was there any Australian suppliers consulted or only European? I'm assuming that's in relation to the equipment.
That was a mix. We did, especially for the wastewater treatment, we spoke mostly with Australian suppliers, but the more advanced, the CO2 recovery was quoted with Australian suppliers as well. But we also tested the quotes against European suppliers as well, so we can compare the difference, right? So biogas plant was directly quoted with German suppliers. The CO2 was Queensland, what they are bringing over from Europe anyway. And the engine is also coming from Germany. Yeah, wastewater treatment mainly Australian suppliers. However, the equipment comes from Europe anyway, so there is no way out.
And this is probably a good joint question from Alexander around the value of tallow to red meat processors. Happy to provide my views on this, but maybe Fabiana, if you just give a bit more context. We never diverted any of our primary tallow production or tallow export into this project. It was always third grade or captured tallow from the waste stream, but Fabiana can maybe comment on that. But for us, we were very careful identifying, and probably that's why we ended up with so many capex models and ROI models and financial models, was to make sure that we had levers to pull depending on the value in the market. So we all know that tallow is highly valuable at the moment through renewable sources, and will continue to be, I assume. So we never intended to divert that into this process due to the value in revenue, but it was considered as the stuff that is slightly lower value. It might be DAF capture, it might be third grade tallow or lower FFAs. We did a cost benefit on whether it would be valuable to divert into this process or not. And it also gives flexibility then if, as Fabiana said, the biowind modeling shows a lot of extra capacity. If the if the tallow market was to crash, which it has previously through whatever economic form, it means you then have the ability to divert that into that process. But Fabiana might be able to comment a little bit more about the logic and the maths behind that.
Yeah, it is really driven by the price of electricity, right? So how much you're paying for energy and how much you're getting from tallow. You can always compare in kilowatts, and that's why we did the individual biomethane potential analysis. So we know how much biogas you can get if you divert the tallow in or out of the biogas. So yeah, it's lower grade tallows, and then in a case by case decision. And the same applies for offals. So sometimes you don't find market for offals, or it's something happened, you cannot process them properly. They are really great value in the biodigester, so you can always make that decision. And in the next version of our digital tool that we want to develop in Power BI, we want to have the choice. What happens? You click and you put the tallow and the offals, and you see the outcome in terms of energy and money. And then you can make a decision live, like, okay, this week the tallow is going to the digester. You have a higher demand of electricity for some reason, it's Christmas, whatever. Yeah, that is a tool for making decisions there.
Right, that's a good point. And if you're going to spend that much money on an integrated wastewater treatment system, you want to have that flexibility as well to be able to manage it during times of price changes on your substrates or your co-substrates. And that's a possibility, is it?
Yeah, it is. I had a similar case with a client in Brazil who he had a huge soybean farm, and he had a biodiesel plant in his farm. So when the soy commodity price went down, he would just produce biodiesel. When the soy goes up, he would sell the soy. It's just similar case.
Right. So did you see any other questions there, Chris, Fabiana, Letitia, Lauren? I can't see any extra ones, any questions when maybe we've covered most of them.
I've been deleting all the difficult ones, Matt.
Right. That's why I couldn't find them. Right. Probably we don't have some...
I think we've got them all, unless any of them pop in now.
As you saw, I'm not scared of hard questions. Easy.
I think if you're saying your next step is final investment decision, then that's not straightforward. As I mentioned, there's lots of things to consider, such as co-investment, staging, time frame, flexibility and management of substrates, outputs. A lot of things might go into that.
Business model.
Yeah, so that if you're going to spend that money, you've got something that really manages well over a long period of time. And that's why, Fabiana, we think you've done such a great job in the presentation. Obviously, it didn't have all the finite detail, but we'll make that available some of it in the final report. We'd also like to just thank again Chris Edwards from Binderee Beef for helping us with the project and being the subject site and being involved with ARENA and the ARENA grant. So we'd like to thank ARENA grant for participating as well on the sponsorship of this project, and Fabiana's team and Fabiana for doing such a great job in looking at it. And we're keen to help where we can with further decision-making work, however long that may take. It's not a straightforward type approach to integrated wastewater treatment, but it's one that looks economic in the long term. So if there's nothing else, I'd like to close the webinar, and we look forward to catching up again. Thank you very much.
Thank you.
Thanks very much, Fabiana.
Thank you, guys.